Hi everyone, thanks a lot for joining me on this tour of the wonderful world of code transformation and metaprogramming in Julia. Now, metaprogramming can be a bit of an overwhelming topic, especially in Julia. I think we have a lot of different options, probably more so than many other programming languages, all the way from creating abstractions by using the language normally, which is quite powerful, to almost building your own compilers. And because there's a lot to cover and this is a brief talk, I'm not going to be able to give you a real deep dive into any one of these things or a tutorial, but I hope I can at least give you a bit of a lay of the land, some idea of why these different things exist and what you might want to use for your own project. So I'm starting here with higher order functions, which is more on the just using Julia normally end of the spectrum, and it's not always associated with metaprogramming, but I think it's a really nice way as a starting point of building these kind of DSL-like APIs and these domain abstractions. So here's a very simple example where we take a user-defined function. This one just sleeps for a second. I check the time before and after and use that to time how long the function took to execute. We can all do all kinds of things like this. We can do things before or after function executes. We can execute on different threads, different nodes on a distributed system. We can modify inputs and outputs, call functions multiple times. Here, for example, with the derivative, we can actually change the input, slightly tweak it, call it twice, and then that gives us a derivative. That's very straightforward. So that's a really nice way to build a lot of APIs. A lot of Julia packages are built this way. Particularly, for example, the Flux machine learning framework is all about composing and modifying functions in this kind of way. And this works pretty well. It's very composable. It naturally works with all of the parts of the Julia ecosystem and language. It's very composable, so you can call, you can have transformations from package A and package B, use them together, that kind of thing. That kind of thing is very powerful. But they'll have an obvious limitation. You can't use them to introspect the function that you're given. So in the derivative example, for example, we can look at the inputs, we can look at the outputs, but the function itself is a black box. So we aren't able to look at this function and say, well, look, inside this f there's an x squared. Why do this fiddly approximate numerical process? Why not just write down, well, we know the derivative of that is 2x instead of x squared. That would be nice, but we can't do that with the normal functions approach. So that brings us on to techniques that allow us to do actual code transformations and expect code and look at them. So here's an example of a macro where the idea here is that the macro, instead of getting the result of this expression as an input, which would be 51, it gets the expression itself, just like it was a piece of text source code. So here we're allowed to do a find and replace using a package called macrotools that allows you to do things like pattern matching. And we're just replacing all of the times we see the multiply symbol with the plus symbol. So very straightforwardly, this expression here gets replaced with 10 plus 5 plus 1, which results in 16 when the expression ultimately runs. So that's very straightforward. There's a lot of really nice things we can do this and deep things we can do this. This example is contrived, but actually a very similar one is based on fastmath, which you may well be familiar with. That just replaces, it's like a find and replace. It replaces the multiply and plus symbols and a few others with approximate faster versions. So that's a really useful thing. It's a useful syntactic convenience. But there are more advanced things you can do with this as well. So for example, the jump package is very nice as an example of this. You can see that we're using syntax here, which usually would be a predicate. It would be a test. We would have a specific number called x, and we'd be testing, is it between these two numbers true or false? But actually in this case, we have something more declarative. We're saying we have our model, and within that model there is a variable called x. We don't know what the value is, but it will be somewhere between 0 and 2. And then combining that with jump solvers means you can add other constraints at an objective, which is another declarative equation, and get optimal values for x and y here. Another really nice example is Turing.jl. There are actually a lot of different really nice PPLs in Julia, but Turing.jl is particularly useful in this example. You can see here that what we're doing effectively is to write a program as if it were generating random data. So in this case, we're sampling from a Bernoulli distribution, effectively flipping a weighted coin n times. But what the model macro actually does is it kind of transforms this into what's called a log likelihood function, which instead of producing an output at random, takes an example of such output and tells you how likely that is to have been produced by the original function. And that's really important and powerful when you're doing things like probabilistic modeling. It's hard in many cases to, or unintuitive at least, to write the original kind of log likelihood equation, but to write this thing as a generative process that gets transformed into a likelihood function is much more straightforward. So yeah, macros are really nice, they're very accessible, it's easy to do pattern matching on the ASTs and it's easy to work with. It's nice for little DSLs like this and transformations. Even macros though have some downsides. So the main thing here is that compared to functions especially, macros are not very compositional. If you want to use two packages together, for example, that both provide only a macro interface, you're going to be stuck with compiling, basically generating and compiling Julia code and passing that through the macro expanders of both packages, which is not going to work that easily. So what packages actually tend to do in Julia but elsewhere as well, in other languages with macros, is they will actually provide a kind of function first interface. And so you can build jump models or Turing models by defining the underlying construct yourself very straightforwardly. And the macro is just a kind of convenient syntax layer superficially on top of that, to just add some convenience. So that's actually really useful. It's great, but it does limit what macros can do because sometimes we want to do deeper transformations. Similarly for lexical scope, and I'll show you an example of this as we start to move to more powerful techniques. So you can see with macros that this example, we're replacing times with plus here, but this doesn't work inside of a function like prod, which takes the product of this list at 5 and 10. Of course, under the hood here, we're doing the same thing, we're multiplying 5 by 10. But the macro can only see this very, the snippet of code that's right next door to it. It can't see inside the prod function, the code inside that function, or the code inside the functions that prod itself calls. So this may not return exactly the result that we want. It's 50 instead of 15 because it hasn't translated that times into a plus. So that brings us to a more powerful technique, which is the cassette trick. There's the cassette.jl package that implements this. There's another package, IR-tools, which implements an equivalent construct with a slightly different API. That's what I'm using here. And you can see that broadly speaking, it's the same thing. We have this pre-walk here again, we have a multiply and a plus. And when we apply this, what we're going to find is that it does what we want. So now instead of just looking at this code here, we're actually looking inside this definition of prod and we're seeing that there's a multiply in there. So now the overall function returns 15, 5 plus 10 instead of 5 times 10. So we're actually looking more deeply into the code and transforming all of the code within a given scope, which is really, really powerful and opens a lot of interesting things. In particular, the Zygote automatic differentiation package is built this way. The other thing that's really nice about this is that we actually get our composition back, our functional composition. You'll notice that this foo here is not some kind of weird syntax construct. It is just a function, which means that we can easily compose transformations together again. So we can take two different cassette parsers from different libraries and run them both on one piece of code. Or we can abstract over a cassette parse such that a user never even has to know it's there. So you don't need to know whether a function is differentiated or not with an optimization library, it just works. So this kind of approach is really cool, it's very powerful, particularly in terms of allowing you to easily create transformations that support the whole language in a very general way. Things like differentiation like that. Things which would be possible technically with macros, but which would require you to annotate every function you wanted to be involved in the computation you're interested in. They do have their downsides though. So the problem with this kind of generated function trick is that it happens before we have any type information or optimizations. So what tends to happen when you're doing these kind of transformations is that you end up transforming code which would be redundant if it would be optimized away by the compiler usually. So for example, things like dispatch or tuples which might be elided at runtime and that kind of thing. But by the time you transformed it, it's more complex. And so the more complex code, even though it's still redundant, it's harder for the compiler to realize that and optimize it away. And that's a particular problem in differentiation, for example, because you tend to do things like nested differentiation where you run the transform over and over again on the same code. And that actually will lead to an exponential blow up of the amount of code. So it's perfectly possible to handle that in principle, but the compiler has a hard time with it. So that's something that's a bit tricky, and there's actually, to solve this kind of problem, people actually turn to a completely different way of doing this kind of thing, which goes by a lot of different names. I tend to call it tracing, but it gets referred to within, especially the machine learning community, as building a static computation graph. It gets referred to as stage programming, things like that. And the idea behind this trick is to basically have a kind of a fake symbolic array or number type. There's a nice GIF of this on the PyTorch repo. And you can see how we have these torch tensors, torch arrays, but they're kind of symbolic. So what happens here is that when you do a mapmol, as opposed to just multiplying those two arrays of numbers, we actually get an object that stores the result, but also stores the whole history of what's happened to this particular array. So we can see here within this data structure that gets built, this array here comes from calling the 10H function on this array, which comes from somewhere else. And so what happens here effectively is that we build an alternative representation of our program. It's a lot like having an abstract syntax tree or a fragment of IR or load or typed code, but it's much, much simpler. There's no language features in here, there's just basic arithmetic operations. So what this means is that you're able to transform this very simple code, and all of the redundancy, all of the stuff that comes up in when you're doing a cassette parse is gone. Just the operations, and it's very, very easy to do, for example, a differentiation transform on this code, on this graph. So that works really nicely, and it's very popular, especially in the Python world. It's the only approach you really have. But it's also popular in Julia for good reason. Tools like reverse diff do this, tools like modeling toolkit, symbolic utils, they all have the same approach of having this pseudo array or number-like type that builds up some kind of graph or representation of the code as an alternative to Julia syntax or Julia typed IR. It's easy to do in any language with polymorphism, which is a really nice thing. It's very easy to implement, even if you're not familiar with compiler technologies. It does unfortunately have its own downsides. So the fundamental limitation of this kind of approach is that it does lack support for a lot of important things like control flows. If you have a for loop that, where the number of loop iterations depends on your input data, that will fail. If you have things like print line statements for debugging, or even just using a debugger generally, you're actually going to find that those things execute at compile time, at least the compile time of the DSL, which is the runtime of the host language, whether that's Julia or Python. So a show macro in Julia will show the fake tensor type as opposed to the actual value of the array that exists when you're training a model on your GPU or something. So that's a really, really big downside. There's a lot of usability with problems, even though it's almost in some ways like the perfect way to get to something like XLA as a compiler target. So we have this kind of hierarchy that we've been through at the moment. We start with just the user of the language with functions. We need something slightly more advanced, so we end up with macros, and then we need something even more advanced, so we're kind of veering towards building our own compiler. And then what happens here, though, is we get the split between these two different techniques, the kind of operator overloading tracing and the cassette-style code transformation. And the challenge here is that both of these approaches are good in their own way. In fact, the set of things that they do well and badly are almost completely disjoint. They're just, they're good at exactly the opposite set of things. So what we'd really like to do is to kind of merge the benefits of these two things. And to a large extent, you can already do that. Just build your own compiler, build a parser, build a language syntax, build your own abstract interpretation, type inference, and so on. But what we'd really like to do in the Julia world is to basically get the best of both worlds for these two things by actually being able to plug into the existing compiler and customizing how it behaves. So this is a kind of generalized abstract interpretation that we think can get the benefits of both the tracing approach in the style of JAX and that kind of thing, the Python libraries, and of the kind of cassette, the more Julia-like cassette approach. So that's work that's largely being driven by the compiler team, and particularly Keno. There's going to be some interesting developments to follow up there. It's hard to know exactly how that will look right now, but I will try to give a bit of a preview that shows how this might look and the kind of capabilities that we can get from this based on some more experimental work I've been doing as a package recently. So this is a package called Mjolnir, and it's explicitly trying to combine the benefits of partial evaluation in the sense of JAX or PyTorch, scripts or things like that, and abstract interpretation in the sense of Julia's type inference. So to show how we can get the best of both worlds here, we can show an example like this power function, very simply doing x to the power of n with a loop. And I can show you what it looks like when we trace this using Mjolnir. So what's happening here is that we have x being some arbitrary integer, but we know that n is the number 3, which means that we can run and roll the loop. And so just like in a standard kind of tracing implementation as you'd find in Python or something, you get this linear trace, which is just a sequence of instructions, no control flow, nothing else. We know the loop runs 3 times, so we just get the same multiply instruction 3 times over, things like that. But where it gets interesting is that because this is kind of a compiler integrated approach as opposed to just a pure operator overloading approach, we can actually preserve things in the trace that would be confusing or broken in a more operator overloading based tool. So, for example, if you put a show in here, so let's put a show in here and then specialize on the particular numbers 2 and 3 as our x and n. And what's going to happen is that we get a linear trace again, but we don't have any multiplies because we know what the return value is going to be. It's just 8. But we do get the print line. And we wouldn't have this, instead of running a compile time, this will run a runtime, or we run when you try to execute this code. And in fact, it's also notable here that we are able to handle strings and partially evaluate string operations, as well as just things like tensors. So that's a more powerful approach in several ways. For the exact same reasons, it actually also supports control flows. So in the case that we don't know what n is, we don't know how many loop iterations we're going to have, we'll actually get a representation of this computational graph in SSA form, which does support control flow. And you can think of this as a set of computational graphs that call each other. So this block 2 calls itself with certain arguments, and that defines a loop, which eventually exits with an answer. So to show the kind of thing that this can do, I want to show you some Futamura projections. And what this means is a Futamura projection is a concept of basically taking an interpreter and specializing it to an input program such that you end up effectively with compiled code. And the idea here is to avoid writing a compiler, because compilers are much harder to write usually than interpreters. So we write a very simple interpreter, we specialize it, and we get compiled code. Easy, right? And we can show this working. So I'm going to show it working in a slightly toy case on a language called Brainfuck. This language only has 6 instructions, so it's somewhat like a Turing machine. We have a long tape of bytes, and the only instructions we're allowed are to move slightly left or right, by 1 space on the tape, or to increment or decrement the cell that we're currently positioned at. And it's Turing complete, so of course we can write any program imaginable in this language in principle. It's really easy to write an interpreter for it, which is what makes it interesting for this purpose. It's a good exercise actually to write a compiler or interpreter. In this case, it's about 80 lines, and the core of it is this very simple loop that just checks each instruction and executes the right operation corresponding to that instruction. To show some simple programs with the interpreter, here's just the program that increments twice. The first cell is 2 now, very simple. This is a program for addition, which 1 by 1 shifts values from this cell to this cell and this cell to this cell, so we end up with the sum 13 in the third cell, 5 plus 8. And finally, the most complex example we're going to look at, which is multiplication. So third cell is now 5 times 8 rather than 5 plus 8. So here's what happens when we try to apply Milner, our tracing tool, to this interpreter. We get out IR, which is a bit fiddly to read. So I have translated this back into high-level Julia code. These are exactly the same. If you were to write code type to this code, you get something like this. And you can see that what's happened here is that we have essentially what amounts to a handwritten translation of this code here to this Julia code equivalent. And the way that this has happened is that we have this interpreter loop, but effectively we find that we know how many iterations that loop will run for. We know it will run for 2 iterations. So we can just unroll the loop and replace it with its body twice. We also know we have this if statement, but we know what the if statement will do. The if statement will just say, is it plus? Yes, it is. Do this. And all of the other else if branches are redundant. So we can get rid of that too. And what we're left with after that process is just those 2 instructions. So we still have an interpreter there conceptually, but it's just, we can prove that it's redundant. This works, so this would work perfectly well with a kind of operator overloading tracing thing because there's no control flow in the final program. But the nice thing here is that it also works with control flow. So here's our addition program with 2 loops, and the 2 loops end up showing up in the final program. So what's happening here then is that there's a loop in the interpreter which implements the language level looping construct. But what's happening is that we see that loop twice, we hit that loop twice from here, and we inline and specialize it twice. So this is the interpreter loop specialized on the contents of that particular loop in our program. And that's twice because there are 2 loops. So again, start with an interpreter and you end up with this compiled equivalent. Works even for multiplication when we have a nested loop. And I'm not showing you of course actually here you would get the compiled IR, which is, for this example, is very verbose, there's a lot of it, but it is exactly equivalent to this Julia code, as if it were translated by hand. We can actually show that our compiler is doing something. It's a bit more than just, I can show that this is not just trickier, it's actually improving our performance. So here we have a benchmark of the interpreter running the multiplication function, and we have compile, which produces that Julia code that you saw, compiles it using a val, and then that goes through LLVM in the usual way, and we get a lambda or Julia function, which implements this program that we've written down here. And so the way that's going to work is that we benchmark both of these things, and we find that, of course, the compiled version is a lot quicker because there's no interpreter overhead, there's no parsing and checking this stuff. It's purely executing these instructions in the minimal way possible. And so it's about 1,000 times faster. So this actually even becomes even more pronounced when we do addition. So in this case, we find doing the same thing with our addition program, it's about 1,000,000 times faster. And that sounds almost implausible, but it's interesting to take a look at this Julia function we have here compiled and look at what LLVM is doing to it. Because what we find if we look at this with code LLVM is it's actually compiled down to an integer add instruction. Because what's happened here is that we specialized this interpreter, we got 2 loops out of it, but then LLVM did its own pattern matching optimization and recognized that those 2 Julia loops were actually equivalent to a single integer addition. And so we effectively have an optimizing compiler via an interpreter, a specializer, and LLVM. So that's neat. So yeah, that gives you some idea of what we're aiming for, the kinds of tricks we're trying to do. It's very relevant for the machine learning world where you kind of are in the situation where a sufficiently configured model is almost like an interpreter of your configuration dictionary, but you want to elide all of that stuff and get very fast, GPU or TPU code or something like that. So that's where we're going in future. For now, you probably want to stick to the more typical metaprogramming tools. There are a lot of great resources for that, particularly David Sander's workshops and Jupyter notebooks that he has, as well as, of course, the manuals of the various packages that implement these things in the language itself. I also will have, hopefully by the time you watch this, a blog post which explains the Fujimura projections and Mjolnir in a lot more detail. And so that might be an interesting resource if you are interested in following where that's going. Thank you very much.